Justin Miller, XR College Physics here, and hey, let's look at some more stuff regarding physics. All right, so what are we going to look at? We're going to look at some more forces of tension, but we're going to look at a specific case. We have an object that's suspended, motionless, so no acceleration. But the object isn't just suspended by one cord, rope or string, it's suspended by two, multiple strings. So we're going to have a suspended object. Held in place by two cords, rope, strings, etc. So what do I mean by that? Well, hey, here's an object right here. It's a nice mass. It's just about a kilogram. It's a little bit less. That's okay. We could say that there's like one string right here, and I could suspend it. And right now, if I said, what's the tension in this string? You'd say, well, what's this mass? If I say, well, the mass is 1 kilogram, you'd say that the tension in the string is 9.8 newtons. Why? Because the force of gravity is pulling this down with mg, and thus the tension must be equivalently pointed back up with the same amount of force to keep the net force on this object to be 0, right? Sounds pretty easy, and we've done, oh, what if it accelerates up, accelerates down? We can do all sorts of stuff like that, but we're going to keep it suspended. But instead of just one string, oh, there's two strings here. So if I say, you know what, I want to suspend this by two strings, and there's lots of different ways that we could do it, right? I could have the two strings at equal angles about this horizontal here, about the vertical. So I could pull them out and say, well, there's some tension in each of these strings. Each of them bears a certain amount of the weight of the object and does something else as well. But they don't have to be at equal angles, right? I could have this one over here and this one way over here. We've got this angle is much different than this angle. We could start going like this. I can feel it in my fingers when I start lifting it up like this and having these more shallow angles here, that the force point on my fingers is greater than when it's just like this. So what's that all about? How do we approach something like this? How do we figure out how much tension is in each of these strings, given that we know the orientation of the strings themselves and we know what mass that they're attached to? So we've got this middle part right here, that little bit of string. Well, that little bit of string is completely vertical, right? And that completely vertical string, this little section right here, has to hold the whole weight of the object. All right, so what's the tension in this little tiny piece right there? That's just mg. But then it splits off into these two other strings. And what happens then? The force gets divided up. But there's some other stuff going on. It's just not divided up in equal amounts or even partial amounts. There's other things going on. So that's what we want to look at. So let us just go ahead and do that. Whew, it's kind of a workout there. Not really. All right, so we're going to take ourselves and say, hey, what if we have some ceiling here? And we go ahead and we take two ropes that are connected to a mass and everything's held at rest. So I'm going to take one like this. I'm going to take the other like this. So we got a long rope, a short rope if you want, but they make two different angles. And then we've got ourselves this mass right here. I'll just draw something like that. Say we've got a mass, we've got I was calling it cords. Cord one, I'm going to call it rope now. Rope number one, and then we've got rope number two. So it should be connected up here. And we have that the net force on this mass has to be equal to 0. Mass remains at rest. So no acceleration, no change in motion. There we go. Net force on it has to be equal to 0. So the question is then, what are the forces of tension transmitted from each rope. We figure that out. And the answer is, of course we can figure it out. That's what we've been doing all along, figuring stuff out. Why would we ask questions that there's no solutions to or that we can't at least think about? So this is what we've got. So how are we going to approach this? Well, first off, we got to identify all the forces acting on this mass, right? So let's just go ahead and do that. We've got, number one, we've got the force of gravity, right? Force of gravity is pulling this mass straight down, and we've got ourselves F sub g hat. Fantastic. What else do we have? Well, we've got a force of tension transmitted in rope number one. Let's call it T hat 1. Right here, T hat 1. And then we've got another one right here, transmitted through this rope, T hat 2. And this one should be a bit longer, actually. This one should almost go all the way up. You may say, well, why do you want to make that one so much longer? And you'll see here momentarily. But this is what we've got going on. We've got these three forces have to all add up to be equal to 0. Fantastic. But what are they? They're vectors, right? So how are we going to treat something like this? Very carefully. So let's say that we're told that these ropes make some angle with the ceiling here. So we got this nice ceiling. We'll say that we've got this angle here. I'm going to call it phi1. And we've got this angle here. I'm going to call it phi2. Those are the angles, the short angles that the ropes make relative to the ceiling, horizontal ceiling here. All right, so what do we do with all of this? Well, what do we have to have? Since the net force must be equal to 0, we must have net force, all its x components must be equal to 0, and the net force in the y direction must be equal to 0. So we break things up into x components and y components. That's it. So how are we going to do this? Well, we can start looking at the x components first. This force here has some x component, it's that way, and this force here has some x component, it's that way. So what if we just take those two forces right now and just look at their x components? So we'll say looking at x components. That's a little weird there. But x components, we've got ourselves this. Let me try to draw it a little bit more like what we have there in terms of the angle. So we've got this, and then we've got that. Those look too similar. All right, so I'm gonna go like this. I'll do it, I swear. All right, so we've got something kind of shallow, and we've got something kind of steep. There we go. So this is our T1 hat, this is our T2 hat. It's supposed to be kind of matching that right there. And then what do we do with those? So well, these both have x and y components for that matter. So let's think about resolving these, right? So we translate this down, and we've got ourselves some T2x, some T2y. Translate this down, that over, and we've got ourselves a T1x and T1y. Again, we just said, let's just look at the x components right now. So this is what we're interested in, is these two. Well, we also got the force of gravity in here, right? But the force of gravity is only in the y direction, negative j hat direction. So if we're just looking at the x, we don't really care about that one right now. So we've got this, right? We've got those two. And what do we have to have then? Just put little hats on these. Hat, 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 hat. So by this, we must have that the net force in the x direction is equal to T1x hat plus T2x hat. It must be equal to 0. So the x components of those two forces must add up to be equal to 0. That's it. There they are right there. So how are we going to go ahead and start figuring out that? Well, let's think about this right now. If we knew what this angle was, which I'll call a theta 2, and what this angle is, which I'll call a theta 1, we can easily resolve the vectors t1 and t2 into t1x and t2x, right? Because what do we have? We have that t1x is going to be equal to the magnitude of t1 times the cosine of theta 1, and that'll be I hat. And t2x is equal to the magnitude of t2 times the cosine of theta 2 I hat. So there we go. So there's the x components, or really the x portion of the vectors of tension, the forces of tension of the ropes themselves. So we need what these angles are, right? Should do it with both. We don't know what T1 is and we don't know what T2 is. That's what we're trying to figure out. What is the magnitudes of those two forces? We should know what their directions are based upon these angles here. All right, so what we need to get is that theta 1 and theta 2. Theta 1 and theta 2. How are we going to get them? Well, let's start looking at this right here first. We've got this angle here. I'll kind of draw this out. This little coordinate system here. We've got this goes like this. And we've got this here, and we're told that is some angle phi 1. All right, and again, that's relative to the horizontal there. What angle are we looking for? We're looking for this angle here. That's a theta 1. So how are we going to get theta 1 given this phi 1 right here? Well, this phi 1 is the same as that angle right there. That's it. We got vertical angles, alternate interior angles, however you want to look at it. That angle there and that angle there are the same, because the ceiling is horizontal to the x direction. So if we want what theta 1 is, we've got that theta 1 is going to be equal to 180 degrees minus phi 1. All right, so whatever phi 1 is, we just say 180 minus that, that's our theta 1. Great. And then what do we have? Well, we've also got ourselves this here. We can go ahead and say this. We are given this phi 2 right there, and we want to know what is theta 2. Well, theta 2 is this angle right here. What do we have? We have vertical angles, alternate interior angles, whatever you want. They're the same angle in this case. So we've got that theta 2 is equal to phi 2 on that side. All right, so we've got those two relations. And now we can go ahead and start putting some things together. So how are we going to do that? Well, what do we got? We go back up. We say the net force in the x direction is equal to t1x hat plus t2x hat is equal to, well, t1x hat is going to be equal to the magnitude of t1 times the cosine of a theta 1 I hat, and then we've got plus the magnitude of t2 times the cosine of a theta 2 I hat. Where theta 1 and theta 2 are that and that respectively. So I'm just going to leave them in terms of theta. The point with doing this was that given these particular angles, we're able to extract theta. And that's something that really depends on how the angles of the ropes are referenced. It doesn't necessarily have to be with respect to the ceiling, it can be with respect to a wall. You have to be a little bit careful with those. But our ultimate goal is to write them in terms of theta, and that's approached geometrically, right? We just have to use some geometry to figure out what they are. What does this all have to add up to be equal to? A 0. That's a correct 0. So what does that give us? Well, it gives us that this has to be equal to negative that. And ultimately, what do we get? Well, if they're both I hat directions, so we're not really concerned about that. And we get ourselves that t1 times the cosine of theta 1 is equal to negative t2 times the cosine of theta 2. And they got to be equal in magnitudes, opposite directions if they're going to cancel each other out. One pulls this way, the other has to pull that way. There it is. What can we do with this? Well, this then we can write a relation between T1 and T2. Let's say that we can write this as T1 is equal to negative T2 times the cosine of theta 2 divided by cosine of theta 1. Look at that. If you were to figure out what T2 is, or someone told you what T2 is, you'd be able to say what T1 is. Just like that. You may say, well, we're going to get a negative here. No, we're not. We're not going to get a negative because this angle, theta 1, is 180 minus phi1. It's over in the second quadrant, which is going to be cosine of that is going to be negative. So the negative signs are going to cancel out, and kaboom, we get magnitudes, positive values. Anyways, we get a nice relation here. Boom, that's worth keeping. We still don't know what either T1 or T2 are, but we're on the right track. So that's as much as that we can do with the x direction. So now, look at y components. Well, we got the same picture right here. There's the y component of T1, there's the y component of T2. We got a theta 1, we got a theta 2. The only thing that this picture doesn't have in it is the other thing that has a y component, which is f sub g. All right, so note that these two vectors are pointing upward. Well, we got theta 2 and theta 1 are both in the first and second quadrant. The sign of those angles will be positive. And then we got this one that's in the negative j hat direction. Great, that's negative. In the end, what do we have? We've got to have that the net force in the y direction will be equal to T1y plus T2y plus f sub g. And those all have to add up to be equal to a 0. So how do we get this? The same thing that we did before. We've got ourselves that T1 y hat is going to be equal to the magnitude of T1 times the sine of theta 1 j hat. We've got T2 y hat is equal to the magnitude of T2 times the sine of theta 2 j hat. And we've got f sub g is equal to negative mg j hat. Negative j hat direction. These ones will both end up to be positive. A grand. All right, so from here, we'll just go ahead and start. Start coming from this and saying, well, T1y, we've got the magnitude of T1 times the sine of theta 1 j hat plus magnitude of T2 times the sine of theta 2 j hat minus mg j hat has to be equal to 0. Everything has a j hat in it, great. We can use plus and minus, plus, plus, minus. And what can we do with this? We can write another relation. We could solve this out for T1. We can take this and say, well, the magnitude of T1 then has to be equal to, we'll add this to this side, subtract that from that side, and then divide by the sine of theta 1. And we've got ourselves mg minus magnitude of T2 times the sine of theta 2 divided by the sine of theta 1. This is T1. What do we have here? Well, we've got another expression that gives us how T1 and T2 are related, such that the net force in the y direction has to be equal to 0. Net force in the x direction is 0 condition, net force in the y direction is 0 condition. Those two conditions need to be met. These are two independent expressions that solve for T1 in terms of T2 and angles. What do we do then? T1 is equal to T1. So what? What can we do with that? We can solve this out then for T2, right? So let me put this up here. Come on down. And ultimately, get to this last step here, where we've got a magnitude of T1 is equal to the magnitude of T1. Ooh, that seems pretty redundant. What does that say though? Negative magnitude of T2 times the cosine of theta 2 divided by the cosine of theta 1 is equal to mg minus the magnitude of T2 times the sine of theta 2, all divided by the sine of a theta 1. What could we do with this? Well, once again, we could solve this out for T2. And what do we get? Well, we could go ahead and start multiplying both sides by sine, and condense those down into the tangent function, move that side over, get T2 out of there. We could do some algebra with this. Should we do it? Yeah, why not? That seems like kind of fun, right? So I'm going to go ahead and move this sine over here. Then we'll have sine of theta 1 divided by cosine of theta 1. So that'll be the tangent of theta 1. So I'm going to write this as negative t hat 2 times the cosine of theta 2 times the tangent of theta 1 is equal to mg minus magnitude of T2 times the sine of theta 2. Alrighty then. And then what? Let's just go ahead and take this term, take it over onto this side, and then factor out the T2. So that term will be positive. This one's negative. So we will have ourselves a magnitude of T2 multiplied by sine of theta 2 minus cosine theta 2 times the tangent of theta 1. There it is. What's that equal to? It's equal to mg, which then says that the magnitude of T2 is merely mg divided by this quantity here, which is the sine of theta 2 minus the cosine of theta 2 times the tangent of theta 1. If we know what the angles are and we know what the mass is, boom, we can figure out what T2 is. If we know what T2 is, we can solve that out for T1. Is that the only way to do it? No, we could have eliminated T2 in favor of T1, solved out for T1 to get T2. There's a couple different ways to go about this, but this is completely symbolic, and that's pretty much that. Again, one thing that you really have to be careful of in setting this all up is how the angles are referenced in the beginning. It's the picture that I drew down, how those phi angles were referenced and how they were related to these thetas. So I know that in a Calc 3 class, they do a problem that's basically the same problem. They approach it a little bit different and just call this one negative and call that one positive and use these angles here, which is fine, but you gotta understand what you're doing here. You gotta understand of how you're extracting out the components of the vectors. And doing it like this, using theta 1 and theta 2 reference with the positive x direction, gives you the right sign. You don't have to add something in artificially. But you could, I could call this right here theta 1, but then I'd have to put a negative sign overall onto the x component. And I would be responsible for that. Anyways, these are kind of fun problems. This was much of the work, but usually you're not doing it completely symbolically in a course like this. You're just doing it with some numeric values. And once you get this right here, that just turns into a nice ratio. You have T1 is equal to 0.6732 times negative T2. And once you've got that, then you can start sticking it in here and solving out for the other value. So it's a little bit easier, I think, in the end when you have numbers. But anyways, you go through stuff, you get stuff. I would just say beware of just trying to skip and using this formula here. It can be deceiving. Some different systems have different setups that need to be taken into consideration. Anyways, that's kind of that. Good times. All right, it was fun. Until next, keep my pins fresh. Take care.